So again, we're on section 4.1 now, fourth chapter in your book. Feel free to read along in your book. Your book has some good readings on this stuff, guys. So it's up to you to keep up with that if you'd like to. So we're going to have three things we're going to look to do. First, discover how forces, so an applied force on an object, affects its motion. Two, discover the difference between a contact force and a field force. Okay, contact force and a field force. And the third thing is to interpret and discuss free body diagrams. Okay, we're going to do each of those things today. So again, we're in section 4.1. It's called changes in motion. And we're going to do those three things. First, let's begin. The first thing, forces. Now, here's my definition, okay, and it makes it a little bit easier. Force to me is just the cause of an acceleration. And anytime you have something that's changing velocity, there must be a force involved. For example, for me to walk across the room, for me to start at rest right here and start walking, I push off with my back foot. So the friction between my foot and the ground propels me forward. And then I step again, and then I step again. So when you're walking, you're constantly pushing with a small force. Okay? Every single time you take a step, you're accelerating that leg forward, and then you're accelerating the next leg forward. So if you wanted to think about this in terms of rowing, so if you were to row in a rowboat, right? If you want to move forward, don't you have to push on the oars? And then the oars push the water, which then in turn pushes the boat forward? It's the idea that you're applying a force which causes you to move. Okay? So generally, we describe these as a push or a pull. A push or a pull. Because you can push an object or you can pull an object. Easiest way to think about forces. Next, the units of a force. The units are going to be called newtons, or a single newton, with an abbreviation of a capital N. Capital N. And this is what a newton really is. Let me explain this, by the way, because this can confuse people at times. This is simply mass times acceleration. And the units of mass are kilogram, and the units of acceleration are meters per second squared. Now, this looks like a minus sign in there. Everybody see this right here? When you see that with units, it actually means they're being multiplied by each other. You're going to see it over and over again. Again, see the kg hyphen m over here in this area? When you see that hyphen there, it means that they're being multiplied by each other, those sets of units. Okay, just so you're familiar with it. Why don't you put a dot? I agree. For my own, if you see me write units, I'll write it like this. Okay? But I want you to see that in your textbook, and in physics, you're going to see kg hyphen m over s squared. Okay? Yes. This comes from one of Newton's laws, which we're going to discuss later in the chapter. But just for now, the units of force are newtons, and we'll get into where they come from more later in the chapter. But that is the breakdown of the unit of Newton. Jeff.
So it really is just unit of unit equals kg times mass over s?
S squared. Sorry. S squared. I apologize. S squared. Okay. That's my bad. Paul, you had a question, or was that what you're asking?
Yeah, that's
Sandra, thank you. Stash.
Is the first equation an S or
Here? Right here?
A or an S?
That's an S. S squared.
I thought that was an A.
Sorry, that's an S squared, that's an S squared, that's an S squared. Yeah. A little blurry, I know. Alright, so the other thing to note, and I put a little asterisk here, since acceleration is really a change in velocity, just think of the fact that whenever there's a change in velocity, you have a force applied. Again, change in velocity needs to come from a force applied. If you're driving your car and you hit cruise control and you're going at a constant velocity, your car is not really, or there's no change in, or there's no external force that's going on here. The force between the tires is pushing you forward for sure, but you're not applying any additional force, thus causing you to accelerate. So if you walk or if you move at a constant velocity like this, there's no force being applied really when you're moving at a constant velocity. But when you start to accelerate, when your object's velocity changes, that's when you have a force. Okay, so again, remember, a change in velocity causes a force. That's how I think about it. A change in velocity causes a force. Or, as we know, a change in velocity is really acceleration. If you have acceleration, you have force. Either of these ways are ways to think about this. These are conceptual, so when you have multiple choice on your test, these are the kind of problems you're going to be asked. There's a change in velocity. Therefore, what can we predict about the object? Well, there's a force applied, or there's something with the time period, or there's something with momentum. To have some sort of choices here, but these are things you want to know. Change in velocity indicates there's a force. All right, next. There are two types of forces. Contact forces. Before I actually put this up, let's discuss before I go into the slide. Contact and field. So, Paul, if you wanted to push this chair toward me, go ahead and actually push it toward me in some method. All right. Did you make contact with the chair?
Yes.
So that's a contact force. If I want to pull this table across the room, do I have to actually touch the table?
Yes.
Now,
And then force.
Paul, if I had a magnet, and I was holding a magnet here, and you had a magnet over here, and they were opposite poles, and I moved this magnet closer, what would happen to this magnet?
It would get it closer.
Yeah, it would get attracted to it, right? But are the two magnets touching originally?
No.
They're apart, aren't they?
Yeah.
Yet they're pulled together by some imaginary force that we don't see. That's a field force. So again, we're going to look at contact forces and field forces. Contact forces are self-explanatory. That's why it's actually in the definition. Forces that come from the physical contact between two objects. For example, friction, a push. So if I literally just push something, if I were to step with my foot, I'm using friction to push me forward. Normal force, by the way, we'll learn about this, but normal force is a reaction force. So you know the chair has a certain amount of weight? Well, what causes the chair not from falling to the floor? The floor pushes back up. And you learn that in maybe like middle school, 8th grade, but we'll go over it again this chapter. For every action, there's an equal and opposite reaction, another one of Newton's laws. Well, what's keeping the object, this chair, on the ground? The normal force is pushing back up. So those are examples of contact forces, those ones. Now, a field force, some examples are a force that exists between two objects at a distance. Okay? And I brought this in today to see if somebody wanted to try. Have you ever blow up a balloon before and then rub it along your hair?
Yeah.
You want to do it, Paul? You got long hair there.
No, it's pretty low and clean and nice. His mom told me. Paul has a bow tie touch. It makes the outfit.
Who can tie a balloon well?
I mean, I've been called.
Really bad at tying balloons. So still, I do not pride myself in at all. They seem to like let go and it like once it goes all over the place.
It's a steep acoustic.
As long as there's some air, it's fine.
No, if you ruined it.
Don't blow it. I already blew it up for it.
Oh, come on, we're all men. I forgot how to. You put it in.
Tyson's hair.
Why?
I said you said we're all men in there. I said there's 4 women. That's what's
No,
fun.
I can't. We joke. We joke. We all.
It's like a trick to tie balloons.
You use your finger. I your fingers too. I've been called an entire generation. I use it.
Tie with your feet.
I have this kind of talent.
You know what I do want though? Man, I wanted to bring a hole punch and use shaving snake.
Yo, Jared, you should do that professionally.
Whose hair? Who wants to mess with the hair?
I spent an hour.
Give it a nice little rub. Alright, come stick it to the wall. See if it works.
That really rub it. Rub it some more, Paul. I didn't know. Good point.
Oh, you dropped it. You better have to do it again.
Oh my god.
No.
So what's the problem there?
Oh.
Yeah. Well, that's fine. That's fine. Let's discuss. Why isn't it sticking to the wall right now?
It doesn't have
Some
to.
reason.
There's something wrong, Paul, too.
Okay.
It doesn't use that enough.
Like,
There's a
there's
little bit.
Is there something going on?
Yeah.
What's it called?
What you're doing is you're charging with a static charge. You're putting like a lot of electrons on the surface of the balloon, and then if they're able to stick to the wall, it might actually stick. It's not working here. You know what the easy example is, and I'll maybe I'll bring it next class. You know when you punch holes in a paper, you have all the little hole punches, and then the hole punch machine, you have like all the whole tray full of them. You do this with a balloon and run it over like the hole punch, all the things will stick to the edge of it. And that's what this is an image of right here. This is a balloon right here with all these little like confetti pieces, and the confetti pieces are pulling up. Now again, this is a field force. Notice there's no contact. originally, this balloon is just hovering over the table here in this picture. And these little confetti pieces jump to the balloon because there's a field force that's pulling them. It's not actually in contact. A simple example again is magnetic or electric. If you look at electrostatic or just electric force in general, if there's electric current running through a wire, there's a force field that is around it or that is induced around it.
What's that song about force field?
I don't know.
But yeah, that's it feels so close to you, but
Oh yeah, it's a force field. You're right. I didn't even think of it. Right.
try to relate.
That's my
No,
favorite
that's
song
good,
ever.
that's good. A lot of the time though, I laugh because a lot of songs they make references to like math and science and they're wrong sometimes. And like I'm like,
There's like this one thing.
Oh yeah, all people want it.
And you're like,
Oh, you had a big.
So the last example, guys. The last example is gravity. And think about it logically, right? When you drop an object, there's no contact between the object and this table, yet the table is pulling straight down, or the earth itself is pulling it straight down. So there's a force, and that force is pulling on this simple binder clip. Okay, it's pulling it toward the earth. It's a force field. All right, the last thing we're going to discuss are free body diagrams. Now,
Is this like a different kind of, it's not a type of force?
not a type of force. Next thing. This is the third topic, free body diagrams. Free body diagrams, we're going to notice here, listen guys, focus, are simple ways of representing actions or forces that are acting on an object. For example, this chair right here, okay, it's got a certain amount of weight. That weight is pushing down on the ground. The ground is pushing back up on it. This jacket is pushing down on the chair. The chair is pushing back up on the jacket. Okay? So, how do we represent these? Well, if we look at two things. First, look at figure A here. Figure A shows a car crashing into a wall. It's going to show all the forces in the entire situation. Figure A is called a force diagram. Now, figure B, though, is called a free body diagram. And figure B is what we're going to be focused on this year, and in all physics. You use free body diagrams because they isolate or analyze only one object. So for part A, you're looking at the wall and the car. But look at part B. You're just simply looking at the car. And notice I put in italics in bold here. The forces, or a free body diagram, shows the forces acting on a single object. On is the key word. So, if I were to, let's say, look at a person standing still on the ground, okay, and let's say this person is holding onto a bucket. Okay, the person's holding a bucket, say it's a bucket filled with sand or water. That's it, let's say just that. If I were to describe the whole situation, I would have to look at the ground, look at the bucket, look at the person. But if I want to draw a free body diagram of the person alone, it would look like this. We'll start with just the person. Okay? It would have the bucket being an external force pulling down. So you could have like a force being pulled down there, F1. The person's weight is pulling him or her downward also. So you always draw the weight from the center of the body. So put like a dot there and draw an arrow down and call it weight, or FG. We'll talk more about that. And then in addition to that, what's holding the person from falling to the ground? The ground, right? So the ground applies a force upward from the ground. We're going to call that the normal force, and we'll go into more detail. But this would be an example of a free body diagram, because there's simply the force of the bucket pulling on the person's arm, the body weight pulling on the person down, and the ground pushing on the person up. Nothing else is happening to this person right now. The forces of the ground is pushing up, the body or the weight is pulling it down, and the bucket is pulling it down. That would be your free body diagram on the right. Again, acting on an object, Now, what if we had something like this? An object sliding down an inclined plane. Okay, so you have some sort of a ramp, and the object is sliding down the plane. If I want to start, I start with the object and I just draw the object by itself. Okay? From the center of the object, I want to draw the object's weight. So I'll put a big W there for the weight of the object. Now, what's the only, or what are some of the other things acting on this object? What's causing it to be stationary on that plane?
Velocity. Well,
Velocity.
is pushing it down.
Gravity.
Which is going to incorporate its weight, because the weight is going to be pulling it down in both angles.
So negative 9.4.
Okay, so what else though besides this weight?
This is a friction between,
Yes, good friction. And which way does that friction act? Does it act up the plane, down the plane, off the plane, into the plane?
sort of down, no, down.
Which way does the object want to move?
Up.
This way.
Down. So friction has to act. So friction would be like this, guys. Again, think about it this way. Friction always opposes motion, right? Until you get to static friction, until you get the friction from like tires, and called rolling friction. Then there, the friction between your tire pushes you forward, actually. Okay? Unless you slam on the brakes, then the friction would stop motion. Now, the object here wants to slide down the ramp by default. If I put anything on a slant, it automatically wants to slide, right? If I'm at a good angle, it stays, because friction is holding it up. But watch what happens when I tweak the angle. As soon as I reach its breaking point, it starts to slide off. That means that the weight component along the ramp has exceeded the frictional force acting up. So remember, friction acts opposite motion. Okay? The last thing that's actually happening, and this is the tougher part, the plane itself, whenever there's a surface contact here, is pushing off with, again, what we called that normal force before. Because again, what's causing this pen from not, like, say, literally falling through my hand? What's causing it? Me pushing back up, right? And we call that normal force. Whenever it's a reaction to just something resting, it's called the normal force. So, this balloon, believe it or not, it could fall through the table. It could happen. But the table is so strong that it can provide a normal force. This binder clip right here, it's got a certain amount of weight. How come it's not falling through the table? Because the table can support its weight with a normal force. So the types of forces are going to be the things that we're going to look at this chapter, and we're going to really look at Newton's laws. Is that clear?
Yes.
And again, today was more of an introduction. I knew we had a short period. Your homework tonight, there's 3 questions. They're very straightforward. On page 128, please feel free to read section 4.1, so you can read from there from today. Also, tomorrow, well, you have class tomorrow. Tomorrow, we're going to do section 4.2. So if you want to read 4.2 before tomorrow, feel free to do that. It only takes about 8 to 10 minutes to read these sections, and it really might help you. You know, if you feel any reluctance in class to answer questions, or if you want a little prior knowledge before class, so it clears any questions up. Okay, so again, 4.1 is your homework tonight. If you want to read 4.2. Tomorrow I'm going to go over part 4 of the lab, so it'll give you more time to do it. Please tonight just finish up your problem sets. Again, please just finish up your problem sets tonight. Don't focus on the lab. Okay, do your homework problems, but look at your problem sets.
So, go back to,
Oh, please tuck in your shirt.
oh,